Welcome to Brain Vision.
Okay, so we're doing chapter 26, problem 93. So it says an RC circuit contains a resistor R of 15 kiloohms. It has a capacitor of 0.3 microfarads and a battery with an EMF of 9 volts. Starting at time equals 0 when the battery is connected, determine the charge Q on the capacitor and the current I in the circuit from time equals t to time equals t, or time equals 0 to time equals 10 milliseconds. And it wants to do it at 1.1 millisecond intervals for graphing capabilities. Cool. Make graphs showing how the charge Q and I change with time. From the graphs, find the time at which the charge. Okay, cool. So to figure out how an RC circuit evolves like this, we need to look back at equations 26.6a and 26.8. Okay, so what these show us is they show us the charge as a function of time is given by C EMF 1 minus e to the negative t over RC. They also show us the current as a function of time. It's given as EMF over R e to the minus t over RC. Okay. Now, from this, we can immediately graph these with graphing capabilities. But let's think about the second part first for a second. So it says find the time at which the charge attains 63% of its final value. So if we want the charge to be 0.63 Q final, okay? Well, what is Q final? That's the question. Q final for charge, you can see as t goes to infinity, this approaches to just C times EMF. So this is 0.63 C times EMF. Now we can just plug those in. Times 0.3 microfarads times 9 volts. And that comes out to being 1.7 times 10 to the negative 6 coulombs. And this is our Q, I'm going to call it P for the point we want to find on the graph. Let's do the same thing for current. So IP is now, we want it to be 37% of the final current. Well, again, the final current is given, as the initial current. Final charge with the initial current. The initial current is given by looking at this at time equals 0, just epsilon over R. So this now becomes 0.37 epsilon over R, 0.379 volts over 15 kiloohms, and we get an IP of 2.22 times 10 to the negative 4 amps. So these are the 2 points we want to figure out on our charge and current versus time plots. So from these equations, all we have to do is get an array of t. If you want to use this in Python, you can do numpy dot linspace (0 to 10 milliseconds) and at a 0.1 millisecond in between. This gives you an array, and then you can just evaluate this at each point and then plot it. So I'm going to go ahead and sketch what the plots are going to look like here. So let's draw this charge versus time plot here. So this is time in milliseconds at 0 to 10. And this is charge at 0, and I'm going to say up here is 2.5 microcoulombs. So we start at 0, and this kind of follows this kind of pattern. Okay? And if we want to find the time when, we just find when this equals our QP that we found before, and we should see that happens at about 4.4 milliseconds. Okay, let's plot the other line here. So this is the current. Oh, sorry, this is still time on the x-axis, of course. So this is time in milliseconds from 0 to 10 milliseconds. And now this is current, and this goes from 0 to around 0.6, and this is milliamps. Now this, we start at 0.6, and it kind of decays very slowly along this path. And again, we should see that IP, what we found before, the point that we wanted to find, happens at the same time, which is roughly 4.4 milliseconds. Awesome.